All right, so this is ocean acidification part one. And in this video, we're going to talk about the chemistry behind ocean acidification. Now, before we begin, let's remember what we learned from playing the Carbon Journey game. So first off, we learned that carbon and also carbon dioxide naturally exchanges between all of Earth's spheres. And so a couple of examples of this would be when land plants that do photosynthesis pull carbon dioxide out of the atmosphere into them. And then we can further move them into the biosphere whenever land animals eat those land plants. Now, land plants can also be buried and go through decay and decomposition to form fossil fuels, storing that carbon in the geosphere. And then another route is whenever carbon dioxide from the atmosphere is then dissolved into ocean water, making it part of the hydrosphere. Now, in the game, after the game we talked about fossil fuel combustion, and we talked about how since the Industrial Revolution the amount of carbon dioxide that's been added to the atmosphere has increased drastically, and so the carbon dioxide in the atmosphere now is a huge reservoir of carbon, and so it's out of balance, and so it's trying to get back in balance. And so what it does is it tries to push this carbon into its other reservoirs. Now, also keep in mind that deforestation has taken a lot of land plants away that carbon dioxide normally would have went to through respiration. And so we're decreasing the chances of carbon to go into these other reservoirs. And so that leaves the big old ocean water as a really good place for CO2 to get dissolved into. And now we also learned in the game that because the dice rolls are based off of real life probabilities, that your chance of being outgassed once you enter the ocean is only 17%. And that's not very much considering that other 83% puts you in different places within the ocean, like in ocean animals or just the ocean water itself, even floating around unchanged. We also did an experiment with cabbage juice indicator, and we learned two things by doing this experiment. The first thing we learned is that when carbon dioxide is dissolved in water, it becomes more acidic. In fact, the more carbon dioxide that we add, the more acidic the solution becomes. And then the second thing that we learned was that over time, carbon dioxide was outgassed, and that returns the water to a neutral state. Now, Hawaii is positioned in the Pacific Ocean, and it provides an excellent opportunity to collect data of both CO2 levels in the atmosphere and also the ocean. Pairing these measurements with the pH of the Aloha seawater provides evidence to the claim that increased carbon dioxide in the atmosphere is resulting in higher rates of carbon dioxide dissolving in the ocean. Consequently, that lowers the pH of the ocean. But how does this actually occur? We have carbon dioxide and water. Taking a look at these molecules' electrostatic potentials, you'll begin to understand the driving force behind the ocean acidification process. These areas in red are regions where there's a lot of electrons, and the regions in blue are where there's a lack of electrons. And so the negative ends are slightly negative, whereas the blue ends are slightly positive. So looking at carbon dioxide, it has a nice distribution of electrons, making it relatively nonpolar. However, these oxygen atoms do have a lot of electrons around them, and so that makes the center where the carbon atom is a little bit more positive than the rest. Now, the water molecule is clearly very polar. The oxygen is extremely negative compared to those small hydrogen atoms that only have one electron in it, making it slightly more positive than the rest. And this negative oxygen atom in the water molecule is actually very effective at working its way to the center of this carbon dioxide molecule and starting the chemical reaction. So this reaction mechanism shows that in the first step of the reaction, the oxygen atom on the water molecule donates a pair of electrons to the carbon atom to try to stabilize the charge. However, carbon cannot hold more than its 8 electrons in its valence shell, so these electrons that are already there are then squeezed out and start orbiting around a neighboring oxygen atom. That makes that oxygen atom negative. Now, in this transition or intermediate state, one of these hydrogen atoms that, again, is comparatively really positive to this negative side is abstracted from it, forming this bond. And then when that happens, it leaves electrons that was once being used for bonding to go to that intruding oxygen atom and finalize the bond between the carbon and oxygen to make a molecule of carbonic acid. However, the ocean is full of these polar water molecules, which means there's an opportunity for a lot of chemistry to take place. Notice that the hydrogen atom is very small compared to oxygen and even the carbon atom. This small size, paired with the lack of electrons that hydrogen has at any given time, makes it very easy to be removed from molecules, and even easier when it is a molecule that has other ends of it that are extremely negative, such is the case with carbonic acid. And so in this second reaction, the oxygen on the polar water molecule in the ocean can make contact with one of these hydrogen atoms and very easily remove it from the carbonic acid molecule. Now that hydrogen atom ends up with a positive charge, and it's now moving around in the ocean water freely on its own. We call this a hydrogen ion. The hydrogen ion itself is the acidic component. In fact, the measurement of pH is based on how much of this hydrogen ion is in the solution. So when these hydrogen ions are formed in the ocean, it becomes more acidic. And when it's in cabbage juice indicator, the solution starts changing colors, making it pinker. Okay, let's take a look at this entire chemical process of making ocean water acidic. Both this first reaction and the second reaction in the process are reversible reactions. That means that when water and carbon dioxide react to form carbonic acid can also go through a reverse reaction in which it goes back to carbon dioxide and water. Same thing is true in step number 2. When carbonic acid dissolves into its ions of hydrogen and bicarbonate, that bicarbonate ion and hydrogen ion can reform back into carbonic acid. Now, this is important to understand because adding this is an extra step into that outgassing process, right? So once this carbonic acid dissolves further into ions, there are 2 steps now that the carbon in this molecule has to go through to get back into carbon dioxide. First, it has to go into carbonic acid form, and then that carbonic acid has to react back into carbon dioxide and water before it can leave the ocean. And so the equilibrium constants for these reactions actually are going to give us a clue on how probable it is for this happening. Now, I've got them here listed as K, equilibrium constant, or K values. And something you need to know about them is when K values are really high, and so by a high K value, I mean something that's time 10 raised to the positive 5. That's whenever we have a reaction that goes to completion. And so, for example, water, carbon dioxide would form carbonic acid, and then carbonic acid would stay carbonic acid. And so these are actually very low K values. And so when we have a K value that's something like times 10 raised to the negative 5, that means that the reaction actually never happens at all, or that the reverse reaction is what's favored. And so that's actually the case, thankfully, for both of these reactions. And so in theory, mathematically, based off of these K values, you would have about 588 times more carbon dioxide in the ocean than you would have carbonic acid. Likewise, you'd have about 4,000 times more carbonic acid than you would even have a single hydrogen ion. And so you're thinking, well, okay, well, that's not much. So why am I bringing up all this technical information? Well, if you remember, the larger concentration of carbon dioxide in the atmosphere means there will be much larger quantities of CO2 dissolved in the ocean water, therefore making the formation of these ions more probable, and so making it more difficult for carbon dioxide to be outgassed. But that's assuming that the temperature of the ocean remains unchanged. So let's do a little experiment to see how temperature affects ocean's acidity. Here's the idea behind the experiment. Using cabbage juice indicator, again, I made these 3 samples for observation. So first, I poured some indicator into 3 different cups, and then I diluted each of the sample to help make the color difference more noticeable. After the dilution, it was time for the fun part. I double strawed it, guys. This made it so that I could put carbon dioxide in both containers at equal rates. And it was a good thing I had on some safety glasses because there was more liquid, there was a lot more juice flying out of the container. And then I marked the two experimental cups with an H and a C. This was to label which would be the hot ocean water and which would be the cold ocean water. And again, I left one of these samples behind as just a color comparison. Okay, so to make the cold water, it was simple. I put the cup in the freezer for 30 minutes, and then that put the temperature down to around 40 degrees Fahrenheit. Now, for the hot water, I had to go through some extra steps, and some of them were safety steps. So first, I transferred the solution into a glass jar so that I could microwave it for a minute. Even though the glass doesn't look hot, it is. So I used an oven mitt and very carefully pulled the sample out of the microwave. And then I set it on the counter for 15 minutes. Now, fresh out of the microwave, the mixture was around 140 degrees Fahrenheit. And after 15 minutes of just resting there on the counter, the temperature had dropped. So I put it back in the microwave for one more minute and then carefully removed it back to the counter for 15 more minutes. And just after 30 minutes, I had already seen the results that I was hoping for. And so here are the results. It appears that the reverse reaction occurs best at higher temperatures. And so when at a higher ocean temperature, the equilibrium of this reaction shifts back towards the reactants, allowing for outgassing of carbon dioxide to occur. Whereas a colder temperature shifts the reaction forward to the carbonic acid side. And so no more carbon dioxide could be outgassed, and so that remained dissolved in the solution, making it more acidic. And so what does that mean? That means colder ocean temperatures means more acidic environment, while warmer ocean temperatures have pHs that are more preferred for ocean animals. Okay, we're going to continue this talk about ocean acidification in part 2, so make sure you check that out. And we're going to talk more on how an acidic ocean affects life. If you want to learn more about pH, check out the What is pH video. And if you want to make your own cabbage juice indicator for experiments, watch that video and learn how to make it. Now, if you watch this video and you felt like maybe you missed something and you want to catch up, I highly suggest that you play the Carbon Journey scratch game that I created. Or if you just want to check out some of the video tutorials that explains the carbon cycle in detail. Additionally, these are great references. If you want to learn more about ocean acidification, I highly recommend going to these places. Okay, everyone, and thank you very much for watching.